Hello everyone. Till now, whatever questions we have solved based on beams, all of those were belonging to simple beam. That means whatever structures of beams we have analyzed till now, in all those structures only single beam was involved. But now we are going to analyze compound beams. We know that compound beams is a kind of structure where two or more beams are combined together either by means of rollers or by means of internal hinge or internal pins. So if two or more beams are connected together and the entire structure together is considered as a compound beam. So let's solve few numericals. One such question is given over here. A compound beam is loaded as shown in the figure. Find the reactions at the supports A, D and E. In the structure, in the given diagram of the question, we can see that we have two distinct beams A, B and C, D, E, and both these beams are combined together with the help of a roller at point D. So this becomes a compound beam. Two beams combined together with the help of one roller. Our aim is to find out support reactions at A, at D and at E. We can see that A is one hinge, D as we said is a roller and E is also a roller support only. So we have to find out support reactions at these three supports. Now even if we are given a compound beam, remember these are two different beams, two separate beams, and those are combined with the help of a roller. So we should isolate them. We should isolate the members of the beam AB and CDE, and we should consider their FBDs separately, and then we should solve those. Let's consider the FBD of the uppermost part of this compound beam, that is the part AB first. Let's draw FBD of beam, the upper beam AB. You know that when even in equilibrium also we have discussed this, when there are two or more objects kept one above the other like spheres or blocks, we always prefer to consider FBD of the uppermost object first, which because it has less number of unknowns in it and we can solve it easily. So the same logic we are applying over here, and we are starting with the FBD of the upper part of the beam, that is AB. Let's draw the FBD. As we can see, at A we have a hinge, so let's represent hinge reactions AX, AY, horizontal and vertical, which are applied at point A. Then we have this 10 kilonewton load. We have got a roller support for the upper beam AB. So whatever roller is present at D, it is acting as a support for the upper beam AB. So let's show a support reaction. Let's call that RD, which is given by the roller at point D. And then we have 20 kilonewton load applied at the end B of the given beam. So here we have three unknowns AX, AY and RD. This is the point D, and all the dimensions are known to us. So with the help of these dimensions, we are going to solve unknowns AX, AY and RD. We know the procedure. As far as possible, wherever there is hinge, we are going to apply condition of moment about the hinge point so that the remaining unknown gets solved. And then we use fx0, fy0, summation fx0, summation fy0 conditions for solving AX and AY. Let's write down these dimensions: 3 meter, 3 meter and 2 meter. Let's apply summation MA equals to 0, taking anti-clockwise positive. So we will have minus 10 into 3 plus RD into 6 minus 20 into 8, and that total sum is going to be equals to 0. That's what we are saying, summation MA equals to 0. Let's solve this. So we are going to have RD equals to 30 plus 160 divided by 6. That will be 30 plus 160, that is 190, divided by 6, that comes out 31.66 kilonewton, and RD is vertically upward. So that is the correct assumption that we have made, that roller reaction RD is going in the upward direction. Let's apply summation Fx equals to 0 so that we can find out Ax, and here we can see that only Ax is the horizontal component. To balance this horizontal component, we don't have any other horizontal force existing in the system, so we know that because of it Ax is going to be 0. So we can say that whatever vertical component Ay is there, that component itself is going to be the resultant of the hinge at point A. Let's call that Ra. Now let's apply summation Fy is equals to 0, where we are going to take upward positive and downward negative. Ay minus, Ay is nothing but Ra, we'll mention it later, minus 10 plus Rd, which we calculated 31.66, and minus 20. This total equals to 0. So Ay is going to be equals to 30 minus 31.66 minus 1.66 kilonewton. Now here we have got negative sign for the reaction Ay. We have taken the assumed direction for Ay vertically upward, and for that assumption we have got a negative sign. That means whatever Ay we have calculated, the magnitude is correct, 1.66 kilonewton, but the assumed direction of Ay is wrong. It should be downward. So as we said, the resultant reaction and the vertical component of the hinge Ay both must be the same. So Ra is going to be equals to 1.66 kilonewton downwards. So these are the reactions of the hinge. This is the roller at D, and at point A we have the hinge. So out of two things which we were asked to calculate, two support reactions at hinge A and roller D we have calculated. Now still we have to find out the reaction at support E, and for that of course we will have to consider the lower part of the compound beam, which is beam CDE. Let's draw the FBD. Let's draw FBD of the beam CDE. At point C, again we can see there is a hinge or a pin support. Let's write CXCY, horizontal and vertical components of that. At point D, now for the upper portion of the beam AB, this roller D was acting as a support. So we have shown a reaction going in the upward direction, which is representing support given to the beam AB. But the same roller now is going to act as a load on the lower part of the beam CDE. And this RD we have already calculated, which is 31.66 kilonewton. Now while drawing FBD of the CDE portion, the same magnitude of RD we are going to use, the reaction of the roller at point D, 31.66, but we are going to change its direction. It should be taken in the downward way. For the upper beam, this roller was a support, whereas for the lower one, the same roller is acting as a load. Remember this. So RD, which is 31.66 kilonewton, we have shown. Further, from point D at 2 meter distance, we have got this another load of 30 kilonewton, and then at 2 meter distance further, we have got the roller reaction. Let's call that RE. This is the end E. Here was the point D, and these dimensions given to us are something like this, 2 meter each. Now let's solve this. Let's solve this further. So now, considering the FBD of the lower portion of the given compound beam CDE, I hope on the screen you can see this. Okay. So this is how the structure of the beam appears. We have considered the lower portion CDE. We have considered the lower portion CDE, and whatever roller reaction RD was there for the beam ADB as a support, the same reaction now acting as a load on the lower part of the beam CDE, and we have taken the same magnitude, but we have changed the direction, right? So if at all you are going to draw FBD of the entire compound beam as such, you don't have to show the reaction of the roller, because they are going to nullify each other's effect. The reaction coming from up and reaction going to in the downward direction. So same magnitude in the opposite direction and on the same line, they always cancel each other's effect. So if you are drawing FBD of the complete structure, the reaction of the roller at point D is going to be 0. But after isolation, as we have done here, we must show the equal magnitudes and the opposite directions of the reaction of the roller at point D. Fine. Moving further, let's see how we can solve this. As usual, let's apply condition of moment summation MC equals to 0 about the hinge point. Let's see then. Let's write minus 31.66 into 2. We have taken magnitude of the force and then we have multiplied by the perpendicular distance from point C, and we have checked the rotational sense. It is clockwise, that's why we have taken the minus sign. Remember, while calculating moment, direction of the force has no role in deciding sign of the moment. The rotational sense generated by the force about the fixed point will give you the sign for the moment. We have assumed clockwise is negative and anti-clockwise is positive. Further, minus 30 into 4 and plus RE into 6 equals to 0. Let's find out RE, the reaction of the roller at point E. So we have got 31.66 into 2 plus 30 into 4 divided by 6. So RE, the answer is 30.55 kilonewton and positive. So our assumed direction of RE, which was upwards, is correct. Rather, we can stop here itself, because in the question it was asked to find out reactions at the supports A, D and E. We have solved all these reaction which were asked in the question. Reaction at D, then reaction at A and reaction at E. If at all you want to solve reactions of the hinge at point C, you can apply summation Fx0 and summation Fy0 for the beam CDE, and then you can find out Cx and Cy. And as you can guess, Cx is going to be 0 and Cy itself is going to be the resultant reaction of the hinge at point C. So Cy and RC both are going to be the same in magnitude, right? So definitely you can calculate it further, and you can check what is that answer. Moving to the next question, find support reaction at fixed support A, internal hinge C and roller support D in the given compound beam. So basically this is a compound beam. How do we know that this is a compound beam? By definition, compound beam should be combination of two or more beams. So they should be those should be connected together either with the help of rollers or internal hinge. So now here it is mentioned that at C we have one internal hinge. Let's first try to understand what exactly we mean by internal hinge. So when we say C is one internal hinge, that clearly means ABC is one part of the beam and CD is another part of the beam. So we can isolate the beams only at the internal hinge point C, and we can draw their FBDs separately. Let's see how we can draw this. We can isolate the two members of the given compound beam. ABC is one member and CD is the other member. Now I'm not going into details of the support reactions at A and D right now. Let me just explain what happens when we isolate the given compound beam. When What exactly happens when we isolate the two individual beams at the internal hinge point from the given compound beam. So C is the internal hinge point. Now we have separated those two beams. Here was the end A, and here is the end D. This is the end C, and here the same end C. So we have isolated the two parts of the compound beam. One is ABC, let's call it AC for convenience, and the other is CD. The moment we isolate the two members of the given compound beam at the internal hinge point, we must show the reactions at the internal hinge point C. And we know that internal hinge is always going to have two reactions, horizontal and vertical. Now, for the part AC, if at all I show the reactions Cx and Cy in this manner, Cx going in the right direction and Cy in the upward direction, remember the other part of the beam at the same internal hinge point C, we are going to have exactly the same magnitude as that of this Cx and Cy, but those are going to be exactly in the opposite direction. What do we mean by that? Whatever Cx magnitude we will calculate for the member AC, the same magnitude of Cx reaction is going to be present for the part CD, but it will be exactly in the opposite direction of what we have taken for the member AC. And same for Cy also. Whatever is the magnitude of this vertical component Cy for the member AC, exactly the same magnitude we are going to have for the vertical component Cy for the other member CD, but exactly in the opposite direction. Why we are getting all these reactions, the horizontal in opposite directions and the vertical also in opposite directions to each other, but they are of the same magnitude? Because in the combined format, for this internal hinge, the reaction is always zero. How come? These two horizontal components, because they are of the same magnitude but in the opposite direction, they are going to cancel each other's effect. Whereas Cy, these two vertical components also are going to nullify each other's effect. They are going to cancel each other's effect, and the net effect at the internal hinge, when the two beams are in the combined format, the net effect is going to be zero. Okay, so after understanding this, let's represent rest of the reactions and the loads which are present in the system. Let's first draw FBD, complete FBD of the part AC. Here at point B, we have got a point load 5 kilonewton. It is mentioned that the end A has a fixed support. We know that for a fixed support, there are always three reactions. Two are going to be horizontal and vertical reactions, and the third is going to be a moment. So AX, AY, and the moment M. So these are the three reactions which are existing for the fixed end. We know that AX, AY, and moment, all these directions and the rotational sense, whatever we have shown in the diagram, these are the assumed directions and the assumed rotational sense. We are not sure about these directions. Once we analyze the given beam, once we calculate these values from the answers, if those are positive, we will say these assumed directions of the components and the rotational sense are correct. If we get any answer negative, we will exactly take the opposite rotational sense or the opposite directional. Fine. Now here we can see that how many unknowns are there only in the FBD of the part AC, AX, AY, moment, CX and CY. In all there are 5 unknowns. Whereas we know for solving any non-concurrent system in equilibrium, we have only 3 conditions of equilibrium. So we cannot solve this part of the FBD for the member AC in the beginning itself, because that is not going to be convenient. We are not going to have all the unknowns solved using only 3 conditions of equilibrium where there are 5 unknowns. So let's check how many unknowns we are going to have for the remaining part of the beam, that is CD. We have already shown the internal hinge reaction CX, CY. D is a roller support, so let's have RD reaction, And as we know, this is a UDL, uniformly distributed load, or a rectangular load. Let's locate its equivalent point load exactly on the midpoint of the span CD, which is 6 meters long. So it will be distributed, or rather let's say bisected exactly in two equal halves, 3 meter and 3 meter, and the point load is going to be equals to area of the rectangle. So 6 into 1, that will be simply 6 kilonewton. Let me rewrite this: 6 into 1, that is 6 kilonewton. So these are the forces and the FBDs of the two isolated members of the given compound beam. Here in CD we can see that Cx, Cy and Rd, these are the only three unknowns, and we can solve it easily. So we are going to first solve Cx, Cy and Rd, rather the FBD of the member CD first, and then we will go to the other member A, B, C. Let me show these dimensions, and then we will go for solving FBD of CD. Let's solve FBD of part, or let's say member CD first. As usual, let's apply condition of moment about point C. Summation MC equals to 0. And let's see what we get. Magnitude of the force into the perpendicular distance, checking the rotational sense, which is clockwise here for the 6 kilonewton. So that is minus plus Rd into 6. So what we have here is Rd we are getting is equals to simply 3 kilonewton, and that is positive. So whatever direction of Rd we have taken is correct. As you can see, apart from Cx, in this FBD of CD we don't have any horizontal component, so Cx has to be 0, and we can say that Cy itself is going to be the resultant component of the resultant reaction of the hinge Rc. Now let's find out this Rc. Now here our assumed direction of Rc is downwards, so while applying summation Fy equals to 0, where upward should be taken positive, downward should be negative, let's take Cy negative, because Cy is going downwards here. Minus 6 plus Rd, which is 3, and that is going to be equals to 0. So now what we have is Cy equals to minus 6 plus 3, that is going to be minus 3 kilonewton, and if you have Cy, which is let's say Rc itself, minus 3, so whatever direction we have assumed for Cy in member CD is not the downward direction. Our assumed direction is wrong because we have got minus sign here. The correct direction for Cy, or let's say Rc, is going to be vertically upward. Remember, this is for part CD. Remember, we are solving FBD of the part CD, and there we have solved Cy. Our assumed direction for Cy here in CD is downward, but we have got minus sign for that. That represents our assumption is wrong. Cy is not downwards, it is upward. So automatically, when we are going to solve FBD of the part AC, there the Cy component should not be taken vertically upward, but it should be taken vertically downward. Why? Because in both the given parts, these two Cy components are going to be of the same magnitude, but they must be of the opposite directions to each other. For CD, if Cy is upward, in AC, Cy must be taken downward. So you can correct that. You can, if you want, you can redraw the diagram, and there you can show the corrected direction of the Cy component. Now let me call that Cy component as Rc itself. The Rc component is 3 kilonewton, as we have solved it from the other part CD. And now let's solve it for the remaining unknowns. Let me hold it this way so that rest of the calculation can be seen. Now we have three unknowns, Ax, Ay and the moment M. So for solving these three unknowns, let's use three conditions of equilibrium. Now we can solve this FBD easily. This was the FBD of part A, B, C. So now let's apply condition of moment, let's say about point A. Now here we know that if forces are applied at the fixed point, now here A is our fixed point about which we are going to calculate the moment, and we say the moment is 0. Whatever forces are applied on the fixed point will have 0 moment. We already know that. Now even though this moment reaction is shown about point A, remember this moment does not become 0. This moment is the reaction from the given fixed support, and while calculating moment about any point, the forces which are applied on that point will have 0 moment. But if you have already a moment present over there, or a couple present at that fixed point, that couple or the moment is never going to become 0, even if you are applying moment about the given fixed point. Okay, so remember, for this assumed rotational sense of moment m, which is clockwise, let me write it minus m. Remember, so that is another reason why this moment m doesn't become 0. Then next force 5 kilonewton. So minus 5 into 5 minus, because the rotation is going to be clockwise, here RC, which is 3 into 10, that rotation is also going to be clockwise, so that should be also negative. So what we have here is m is equals to minus 25 plus 30, rather that is minus 30, so that will be minus 55 kilonewton meter. Remember, you have calculated moment, it has to be in kilonewton meter, but now we have calculated it with a minus sign. What exactly this minus sign is representing then? Our assumption for the rotational sense of this moment has gone wrong, so that's why we are getting minus sign over here. So let's correct the moment which is present for the fixed support of A as 55 kilonewton meter. Let's remove that minus sign and now correct the rotational sense. Our assumed rotational sense here is clockwise. Let's make it anti-clockwise. Now the remaining two reactions, AX and AY, again here we can say that AX is the only horizontal component in the entire FBD, so AX is going to be 0, or rather you can say summation Fx is 0, and then you can apply all the you can check all the forces, and then you will get to know that AX has to be 0 only. And because AX is 0, we will say AY itself is going to be the resultant reaction of the hinge, that is RA. Sorry. And now let's try to find out this RA. Our assumed direction for AY in this FBD is upward. So while applying summation Fy equals to 0, let me take this RA positive, then minus 5 and this minus 3, that is equals to 0. So we have got RA equals to 8 kilonewton, and with our assumed direction correct. So at the end, at point A, if I have to show the total all reactions existing for the fixed support, I can show it this way. If this is the end A, we have RA which is 8 kilonewton vertically upward, and then we have got a moment which is anti-clockwise with rotational sense 55, with the magnitude 55 kilonewton meter at the rotational sense as we checked anti-clockwise, and this is the total reaction existing at point A, and that is our final answer. So this is how we have to deal with compound beams, and yes, we will have to always isolate the given compound beams, and then we'll have to find out those internal hinge or the roller reaction which is joining both the given beams together in a compound beam. So that's all from the chapter compound beam. We will, in the next lecture, we will start with the next chapter. Thank you.